So I manually came up with those numbers, but I would really like to think that you could do this yourself. So if you're coming to me saying, Dr. Gasser, would you please interpret what all these numbers for me mean? I'm going to tell you no. I don't even remember what they mean, first of all. I understood it at the brief moment when I wrote these numbers down. But here's what I did. I looked at this picture, and I said, okay, piece number 0 has one at location 1, 3, and 2, 3, and 1, 4, and 2, 4. 1, 3, 2, 3, 1, 4, 2, 4. See that? Piece number 1 has them at 1, 5, 1, 6, 2, 6. 1, 5, 1, 6, 2, 6. So there you go. The numbers are all here. So copy, paste, think about it, fix it up. There, it's all done for you.
So you could do like a current state, proposed state with zeros and ones, and then just add them together.
That's a great way to do it, yeah. If you're comfortable with bit twiddling, you can do it really efficiently. A warning about Java. Java does not support unsigned integers. And so when you do bit twiddling, that last bit can really throw people off. If you just think about it as you only have 31 bits to work with instead of 32, then it usually works out. Or if you actually know what you're doing, you can do it even with signed integers. Just don't forget that that last one has kind of weird meaning when you print it out. And yeah, bit twiddling is the real hardcore computer science way to do it. A 2D array of chars, you're probably wasting 7 out of 8 bits per 1 and 0, but memory's cheap, computers are fast, who cares, right? Yeah, when I did my implementation, the one that was really fast, oh wait, that was really fast in the previous assignment. I did it with chars, it worked fine, so did almost everybody else. A couple of the hardcore students did it with bit twiddling. There's work too. Yeah.
Okay, probably a dumb question, but clearly that's fine, but I want to clarify. Whenever we print out the steps, X is a left-right motion or up-down motion?
X. I usually think of X as referring to a horizontal axis. But I don't understand what your question is asking.
Yeah, that's what I'm asking. Well, because in the GPU class and an image, and X is actually a column, and it messed up a lot of my homework.
Ah.
So I'm just making
In
sure.
linear algebra, they always put the row number on the matrix first, and then the column second.
Yeah.
And in graphics, they always put the horizontal position in that direction first, and the vertical position in that direction, which is the opposite of what you do in math, which is that direction next. Wow, that came out confusing. Matrices, row then column. Graphics, horizontal position then vertical position. Math, horizontal position then vertical position. And none of them are correct. They're all wrong because there is no right in this realm. It's just how you want to do it. Yeah, in fact, you can mix everything up in your code as long as you're consistent, and it will all work out. As long as, so if it makes sense in your head, go with it.
It needs to make sense to the graders. I need to know what
Yeah.
like it's
Well,
not arbitrary. I need to know what.
Oh, you're asking about these numbers.
Right.
This is what the grader's going to look at.
Right. So the x coordinate would be a horizontal motion.
Okay.
Y would be up down motion. Just make sure I get this straight.
Yes. I'm saying the first number is horizontal.
Okay.
The second number is vertical. And let's use this numbering system. I have, in very faint letters that you can't quite see here, 0, 1, 2, 3, 4, 5, 6, 7. This is the first number. This is x. Is where it is on here. And wait a minute. Forget what I just said. Let's not use these numbering systems. But we'll use the same concept. The first number, if it gets bigger, it means the piece moves that way. The second number, if it gets bigger, it means the piece moves that way. I'm going with graphics format because I was thinking about graphics when I was writing this graphics visualizing anything? That's actually a really important question you just asked now that I think about it. Thank you for asking it. Are we clear? When, in your answer, when this 0 changes to a 1, that means piece number 0, because I'm in column 0 here, moved to the right. Right there. And right here, when this 0 turned into a 1, that means piece number 10 out of 11. Oops, I just switched from 0 index to 1 index. Piece 9 out of up to 10 moved that direction 1 move unit, 1 square. Okay. Now here's another point about this problem. We've got a starting point. It is represented by this. Or it could be represented by all those numbers down there, however you want to represent it. What is the goal point? How do you get the goal point?
The first two numbers are set, and the rest of them are unknown. So
Exactly.
whatever state gets to those first two numbers working.
That was supposed to be a trick question, and you nailed the answer. So, good job. Basically, there is not a goal point, because we know the red one has to be right there, but I'm not telling you where all the others are. And so the goal point, whatever it is, you can only recognize it by checking whether the first two numbers are, what, 5 minus 2. Whoa, 4 minus 2.
But it's relative.
Because it's relative. So let's talk about that. Let's encode this state. What is it? How do we encode this state right now? I'm going to say 0, 0, 0, 0, 0, 0, 0, all zeros. Does that bother you?
Yes.
Little. Yeah. Okay, I bet it does. How is this one at 0, 0? Because it hasn't moved. What about this one? Because it hasn't moved. Where would you like this one to be? Do you think this is at 1, 3?
Yes.
Yeah.
And then I'll just-
Because you go with top left corner? Okay, well where's piece 8?
8, 5.
Is it at 8, 5 or is it at 7, 5?
What's where the number is?
Okay. We could do that. We could translate this and go where the number is. We could. No, here's why I don't want to go with that. I want you to think about this in terms of relativity, and you can. It's not that hard. And that's kind of important because, what am I saying? Basically 0, 0 means put it where it's at in the starting position. And you can code that up just as well. It doesn't really require a lot of rethinking. That didn't come out as elegantly as it was in my head. I'm trying to figure out how that was in my head. I mean, really a number system is just a number system. You can put the origin wherever you want to. You understand that?
Mm-hmm.
Suppose we're going from here to there. Where's the origin? Well, all I'm doing is I'm taking the origin and I'm putting it at your starting point. I'm calling that 0, 0, 0, 0, 0, 0. So because I called it that, so it is. I moved the origin to this location. And that means it's offset by whatever location feels more natural to you. But you can search through a space no matter where the origin is all the same.
Can I make an argument for not using all zeros as the origin?
Yeah, you can make an argument, sure.
Whenever you're comparing two pieces to see if they overlap,
Uh-huh.
every comparison between two pieces would have to have its own transform to see if they overlap, which means you need like 110 different comparators for it.
Whoa. You wouldn't need 110 comparators. You would need basically this table. So here's what I'm saying. When you're writing your, you're going to write a method named something like, is this legal? And is this legal will pass to it a state, meaning 22 numbers, right? And those 22 numbers will come in, and is this legal? This job is to return true or false. right? Now, what it will do is it will first create this array of 10 by 10. Don't allocate the array right at that moment. Have one already allocated and just use it over and over and over, okay? You know that just from coding style, right? Don't allocate things over and over and over if you need to keep reusing it. So you have this buffer of 10 by 10 already allocated. And now your job is to start putting X's in there, or putting whatever you want to in this buffer where the pieces go. And those 11 numbers, 22 numbers, are going to tell you where to put them. So you'll take the first number, and you'll basically add the first number to the X location of each of that piece's 3 squares, and put that in your buffer. And you'll take the second number and add it to the vertical location of each of the 3 squares, and now you've got a spot, and you put an X there. And you'll basically run through this list of numbers and fill up your table. And if you ever wrote an X in the same spot twice, you'll return false, else you'll return true. So that's the implementation of it. What will have to happen, no matter how you code it up, is you're going to have to add these numbers to all of those 22 numbers. That's how you implement it. Now, my question is, how does that get any simpler if we use some other coordinate system? You could potentially make it so you don't have to worry about sign. That state never goes negative, and that could be a bonus. But then some of these would be negative. Anyway, I've told you how to code that up. Does it gel in your head? Do you see how you code up this is it legal function? Okay. Really, coding up is it legal is the hardest part of this assignment. If you can code that up, then you need some way to iterate over your 44 possible moves, and for each one call is it legal. And if it's legal, then you actually do push its child back into the queue. You're going to have a copy constructor for your state, or some way of making a copy of your state so you don't mess it up. Plug it into uniform cost search, run it through, get the answer. Yeah.
So going with the system, everything that's already on the page, that would mean that the final state we're wanting for 0 would be 4, -2, right? I think it would be. My main question is, when you have an example of output, it
Yes,
only has
4,
zeros,
-2.
1s, and -1, but that's completely arbitrary. I mean, that's by accident, right?
Yeah,
Okay.
I'll tell you where I got this output. I ran this code right here, which makes random illegal moves. I clicked my mouse a whole bunch of times and printed out the state each time, and this is what it produced. So this is random move generated state.
So we're going to want the first 2 coordinates to be 4, -2 at the end.
That is correct.
Okay.
In fact, that's the goal. If this one's a 4 and this one's a -2, you have arrived at this piece being right there. So now you know how to recognize the goal. What in 22-dimensional space, what does the goal look like now?
Well, there's numerous
It's
possibilities.
a 21-dimensional shape.
It is.
It's a
It's a
21-dimensional surface in a
Two of the
22-dimensional
dimensions
world.
are fixed,
Right.
and all the other remaining dimensions extend to infinity in both directions. So in fact, that's just really hard to think about. Imagine 3-dimensional space. Take away 2 of those dimensions. Fix all. 2 of those dimensions are free. What do you have?
Line.
You have a line. Okay, now add a time dimension to it. So now we've got 4-dimensional space. What does that line become? It's kind of a plane that extends through time, right? Keep doing that 20 more times. And now you've got what the goal is. It's basically this volumetric, it occupies 20 dimensions in infinite directions all the way. It just happens that there's these two extra dimensions that we want to get just right. And our starting point is a point in 22-dimensional space, and we're going to snake through it until we hit this massive volumetric goal. And if you can think about it, we're happy with any goal that defines only those two dimensions. But we're going to have to move in all these dimensional directions in order to get those two just right. And that characterizes this problem. Now, all the illegal moves you could think of as being walls. So effectively, in 22-dimensional space, this is a maze. Did you follow that? Because there's a whole lot of directions you can't move in. Is that not like a maze? So if I'm in 2D space, 3D space, and I'm going through we'll say a corn maze, because you've all been through corn mazes, right?
Yeah.
If I were blindfolded, I'd like to think I could move this way or that way or that way or that way. But in reality, if I try, I bump into corn. But I maybe can go this way. No corn. Go a little farther. Ah, there's corn. But now I can go this way, right? That's kind of what this thing is doing, is in all these 22-dimensional dimensions, can I go this way? Nope, corn. Can I go this way? Yes. And so there's always a couple of directions it can go, but most of them are blocked off. So essentially, this is a maze running problem, which is perfectly well suited for uniform cost search. So your uniform cost search implementation will solve this problem beautifully.
How would you use A-star search for this one? Is
Okay.
it possible to use it?
Yeah, in fact, I want you to know that, so I'd like to review really quickly what is A-star search. More specifically, let's do it in this context. Somebody remind me, what is A-star search?
Uniform cost search, but the cost is augmented by your distance to a goal state.
Exactly right. The only difference between A-star and uniform cost is how we sort the priority queue. In uniform cost search, we sort the priority queue by the cost that we've done so far. In A-star search, it's the cost of what we've done so far plus however far we think we are from the goal, or how much cost we think there's still going to be to get to the goal. In that case, however, you have to be really careful never to overestimate the distance to the goal. If you do overestimate the distance to the goal, then A-star search no longer guarantees to be optimal. Do you see why? Somebody tell me why.
Because the frontier will be going backwards away from the goal.
I think so. Think about it this way. Imagine you're right next to the goal. The goal is just right in front of your face, and you have one action left to do. Yay, I win. What's the distance to the goal?
0.
Close to 0, 0.00001, something, or maybe it's 1 if we're in integral spaces. Imagine I overestimate that. What's going to end up happening? I'm going to try something else. I'm going to try these other things. And imagine I keep doing that. I don't know why I keep doing it. But as long as I keep doing it, something else is going to find the goal first. And what that means is I'm not going to go to the goal from right here. I'm going to get there from somewhere else. So at least in that really extreme, weird case, overestimating the distance to the goal messes things up royally. I'm trying to think if that's the best example. Well, at least at the last moment, if we overestimate it, it prevents us from taking that final step. If you overestimate the distance, it does shuffle things in such a way that by the time you reach the goal, it's not necessarily optimal. Okay? As long as you only underestimate the goal, then when you're right here, let me think about that. There's a distance of 1 between me and the goal, and I'm going to estimate that there's a distance of 0. All I'm relying on is my cost. So in the worst possible case, I'm still going to get pushed into that goal as soon as everything of the same cost is run out, right? Okay, that's the case I was trying to think of. So you're right up next to the goal. The estimate starts mattering less and less and less the closer you get to the goal, right? So as long as you always underestimate it, A-star becomes uniform cost search. But if you overestimate it, all bets are off. You might not reach the goal. Yeah, you might go the opposite direction. You'll chase whatever the priority queue happens to do. But as long as you underestimate the distance to the goal, you'll never go wrong. Okay, so
So how do we know when we get piece 0 to where 10 is, that the way we got it was the optimal path of getting there?
Okay? Because you used uniform cost search to find it, and uniform cost search is optimal because I said so, and because intuitively it has to be because it searches with uniform cost.
I was more of saying, how do we make sure our code is
Well,
correct?
how do you make sure it's correct?
Yeah,
That's kind of what assignment 2 is all about, is make sure it's correct and then just use it again. I wouldn't really know how to tell for sure,
okay.
per se.
Write the solution up to the game and see if it's the best way. Have you done
Yeah. I still want to get to how to use A-star search with this problem, but let me answer your question first.
When they print out your steps, can you just move the pieces and the steps that they list them, and then if it works out, you're right?
That will tell you whether or not your solution is valid, yes. That will not tell you whether or not there is a shorter, whether there exists a shorter solution.
Oh, okay.
Here's why we know uniform cost search is optimal. If there existed a shorter solution, we would have found it. And why do we know we would have found it? Because we tried everything. I mean, that's what we did. We were systematic. That's what uniform cost search is. You iterate over every action from every state, and you try them all. And you expand them with uniform cost. So if something had less cost, it would have found the goal by expanding with uniform cost first, right? So that kind of proof is the kind of proof we balk at in most of science, right? I'm sure there's no resolution, because if there was, I couldn't think of one. That's just not a proof. But in this case, it is, because we thought of everything. In this universe, there is nothing else to do. The only things you can do are those 44 possible moves to every piece. So if there was something else, we would have tried it. So if it doesn't find it, there isn't one. And that's the proof. You can see that in your 2D terrain map, right? I mean, you have these expanding uniform cost regions. You know your solution was optimal, because intuitively, if something else was optimal, you would have found it. Well, same here. So as long as your code does what you think it does, it's optimal. Okay. Well, now let's turn this from uniform cost search into A-star search. We have to estimate how far we are from the goal. Go ahead, give me an estimate. How far are we away from the goal right now in this state? What?
4 -2.
Okay. Yeah, we're at least 1, 2, 3, 4, 5, 6 away from it. Because if everything else disappeared, it would still take 6 moves to get it there. And you couldn't get it there in less than 6. So if you want to measure the Manhattan distance to the goal, I think that guarantees to be an underestimate. That cost is less than or equal to the true cost. So that's a valid heuristic. I haven't even defined the word heuristic yet. I need to do that. There you go. Can anyone do better?
3.
That's worse. It depends how you mean by worse. 3. 3 is less than 6. Let's say it this way. What's a really easy way to always underestimate the distance to the goal?
Say it's 1.
Always guess 0, right? If you guess you're already at the goal, what will happen if your heuristic says always 0? Will your solution be optimal?
Yes.
Yeah. If you use A-star search and you estimate your distance to the goal is always 0, you will get the optimal solution.
Isn't that just uniform cost search?
Because it is uniform cost search. That is exactly uniform cost search. So in other words, A-star search, the awesomeness of A-star search depends on the awesomeness of your heuristic. A heuristic is when you guess how far you are away from the goal. The term heuristic covers is much broader than that. In the context of A-star search, the heuristic is how far you are away from the goal.
Say 8.
Yeah, if you consider this black piece, then we know it's going to be at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can say it's at least 10 by considering only that black thing and these other black things. But I could do better than that. If I consider that black thing and the location of this green one, I'm going to have to move that one out of the way to move it. So it's gonna have to be at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So at least 14 is the best heuristic, right? But what if I also consider that blue piece? Now, do you see where we're going with this?
You have to solve the puzzle.
Eventually, I have to solve the puzzle to get the heuristic. And the whole point of the heuristic is to speed up how long it takes to solve the puzzle. Thus, the paradox of A-star search. The only way A-star search is useful is if you can estimate reasonably well how good the goal is. If your estimate stinks, A-star search is not much better than uniform cost search. If your estimate is great, well, you've already solved the puzzle, so what's the problem? In a lot of cases, such as in a video game, getting my character from here to there, if I just measure the Euclidean distance from here to there, that's a pretty decent estimate, right? I mean, maybe I have to go around a tree and around somebody else, but it's going to be kind of close to the straight line distance. And so it turns out A-star search really rocks in 2D space when you use Euclidean distance as the heuristic, because you know it's going to be at least that far to the goal. In this problem, well, I have to ask, what's your heuristic? If your heuristic is the vertical distance between this thing and the top, that's a really cruddy heuristic, right? I mean, yeah, we know it's going to take at least 2 moves. True, it turns out it's going to take something like 146, and 2 does underestimate it. So A-star will improve upon uniform cost search in this problem by a super, super teeny tiny amount. Yeah.
If you're able to move more than one space in a direction, does that still count as one move? So if you move 2 down, does that count as one move or 2 moves?
In this problem, we're going to say that's not a possible, that's not a considered action. If it were, you could do things like move this one 26 spaces down. And in fact, your isValidState function would say, yeah, that's valid because it didn't stomp on anything. And so you could just teleport all the pieces out of here and then move the red one up.
We're just moving
and
through
you've
the
got it.
23rd dimension.
Yeah, so that would be, well, that would be more actions than are valid. Your 4 possible actions for each piece are 1 step in each direction, where 1 step means that wide, if you're on the screen.
I think he was saying not, considering still bounds and everything, it has to be a legal move, but like block 10 could move 2 left. He was just saying, does that count as 1 move? Orange one,
Yeah,
orange.
the orange
So,
one.
he was saying, does that count as 1 move?
Yeah, one
that
possible
counts.
move is go here, and the next move time you could do that. But time passes after you go 1, so yeah, you're right, this one can go 2 to the left, and then it can go 1 down. That's 3 moves. And you're trying to minimize moves, so if you don't have to move it down, move it up, is the problem there. In the actual Professor Layton problem, these 2 black squares didn't exist because you're trying to get this red one out, but it prevents you from moving these pieces higher than this point. That just seemed kind of confusing to explain, so I just blackened the top here and presented my version of the puzzle, in case you're wondering. Because that way we don't have to think about, I don't have to add an extra rule that says this piece can't move up there. And that works for me. We could have said the red one has to actually get on top of that black one, but that's illegal, so in my rules. Yeah, we could do all kinds of weird things, but this is the puzzle I invented, so this is the puzzle you have to solve. Okay. And by invented, I mean ripped off from Professor Layton. All right. Do you see that A-star search just isn't going to help with this problem very much? Okay. What about maze running? Let's go back to 2D space because we can think about it a little better. Now we're in 2D space. Let's see, 3 o'clock, 15 minutes. We're running a maze. How's A-star search going to do for you? Again, it's what's your heuristic? If your heuristic, the usual assumed heuristic in A-star search is take the Euclidean distance between your location and the goal.